On this video, we're working out of our Taylor Series packet, and we're going to talk some more about error bounds. So the first, we're on about page 6, I believe it is, in your Taylor packet, and we're just going to go over the idea of what we mean by these error bounds, and then we're going to jump into the Lagrange error bounds and see how we can use that and do some examples there. So as we can see here, we can approximate any function with a Taylor polynomial, and we'd like to know how good that approximation is. So what we're doing here is looking at sine x, and our Maclaurin series for sine x, we hopefully know, is those odd powers over odd factorials that alternate in sign. So you can see listed here that we have y1 as sine x, and you can do this with us, and y2 we have those the fifth degree or fifth order Taylor polynomial centered at 0 for sine x. So you can see those are written down here in y2. Notice that we have unhighlighted these, but this is highlighted where we have the absolute value of y1 minus y2. So what we're going to see on our graph is this error. This is just showing us visually the graph of the error. So we're going to, and as it says in number 2, turn off the y1 and y2. Now for your window, we can set it like we see here. We're going to go, x-min and x-max are going to be -3 to 3. And notice the scale here is 1, but the y-min and y-max, we're going to go from -0.01 to +0.02, and our scale is going to be 0.01. So on this graph, this is going to be 0.001, and this is 0.002 on the y direction. So when you graph this, and we're going to see now our difference, our y2 minus y1 in absolute value, you should get something that looks like it pretty much hugs the x-axis until you get just before that first tick mark, and then it's going to kind of go up there. And likewise, on the left side, it's going to be symmetric. It's going to take off and do that. So what we are interested in is what's the interval for which these results are fifth degree Taylor polynomial is within 0.001 of the actual value of sine. So if we graph, we're going to turn around then and graph y4 equals 0.001. So you're going to get then a horizontal line that comes right across here. We can use our intersect, so second trace for the calculate menu, find the intersection of these two, and we are interested in then what are those x values. And when you do those, I believe you're going to get that the difference is going to be less than 0.001 on the interval from -1.263918 to a +1.263918. So then what we're going to do, that's pretty good accuracy on that interval. Now we're going to add another term into our polynomial y2. So that means up here, we're going to now add in our minus. So we're going to go minus x to the 7th over 7 factorial. So that's going to be one more term. And then make sure you turn off the y2, because once you add something to it, your calculator will try to highlight that equal sign again so that it'll graph. But then when we graph, we'll see how that improved our interval, and you should see something now that looks like it's going to hug the x-axis a little farther until you get somewhere about like this as your interval. And so then we can repeat our process and try to find these points of intersection. And when you do that, I believe you can see that we have extended now our interval where we have accuracy at least 2.001, and it's going to be a negative 1.392166 to a positive 1.932166. So you can see we're adding an extra term in our Taylor polynomial, extends that interval of convergence on the accuracy that we would like to have. And so you can do that again. And I'm not going to do that. So what happens is the interval increases each time. So the interval, we say, of convergence, convergence increases. And how many times could we do this? We can do it forever. Oh, and I do have that. It's actually going to be negative 2.630384 to a positive 2.630384 is how we're going to extend that interval from what it was after our next term was added. Okay, so obviously this would be very time consuming, but that's why we get our Taylor's theorem. So here again is our Taylor's theorem. We can see it written out in our packet, and it's telling us that here is that remainder term for R sub n. That's R sub n is the remainder term for an nth order Taylor polynomial. Okay, so let's see what it wants us to do. We want to prove, this is one use of our Taylor's theorem, prove that this series will converge. It's our Maclaurin series for sine x, and we want to prove that it converges for all x. So write the formula for the remainder theorem. So R sub n is going to be, it's going to look like that next term, the n plus first derivative, only instead of being at 0, it's going to be at some unknown number. And then we're going to have our x to the, and we plug in n plus 1 there. That's going to be a 2n plus 3. You see why that works? 2 times n plus 1 plus the 1. It's going to make that be 2n plus 3. And that's going to be 2n plus 3 factorial in the denominator. So what is the maximum value that any derivative of sine can take? So remember, our function is the sine function, and any derivative of a sine function, so let me erase that. So any derivative of sine x is going to be either a positive or a negative sine x, or a positive or a negative cosine x. And we know that the largest, the maximum, that the absolute value of an nth degree of sine x can be is going to be 1. So it has to be less than or equal to 1. So then that allows us to replace in our error term here, we know that R sub n of x is going to be less than or equal to, we can replace all of this with a 1, and so it's going to be x to the 2n plus 3 over 2n plus 3 factorial. Now, as we take the limit as n goes to infinity, remember the way this works is you pick a number for x first. Once you pick that number for x, it's fixed. Then you let n go to infinity, and eventually that factorial is going to outpace that exponential, that power function, and so our limit as n goes to infinity of R sub n of x is going to be 0. And since the error goes to 0, that means the series is converging to our function sine of x. Not very satisfying, but that's how the proof goes. Now, here's more like what most of the problems we're going to have to do is going to look like. So in this case, what we want is to use our remainder theorem and to determine how closely the fourth degree polynomial, Taylor polynomial for cosine x approximates the true value of cosine x on this given interval. So we know that cosine of x is going to be the even, so it's going to be 1 minus, and then we have x squared over 2 factorial plus x to the 4th over 4 factorial, and that's where we're going to chop it off for our 4th degree Taylor polynomial centered at 0 for cosine of x. And we're centered at 0, we can see, because our interval is centered at 0. Now, we could use r sub 4 of x, and that would be fine. We can, if we like, steal an extra kind of order of accuracy here, because we know that there is no 5th degree Taylor polynomial for cosine x when it's centered at 0, because the fifth order, the fifth derivative of cosine at 0 is 0. So we could go to an r sub 5 of x and get one little extra boost from our factorial in the denominator, which will allow us to get a little bit more accuracy that way. So if we take advantage of that, then our r sub 5 of x is going to be the 6th order polynomial at some unknown number times x to the 6th over 6 factorial. Hopefully that makes sense. Now, as we've argued before, the largest that the absolute value of the 6th derivative at any value for a cosine is going to be 1. So we can now say that our r sub 5 of x, this error bound, is going to be less than or equal to, and we're going to replace this by just a 1. So this is the idea. So that's now taking us to x to the 6th over 6 factorial. Now we know that on this interval, the largest that x to the 6th can be is when it's the furthest away from 0. So that's going to be at 0.5 rather. So we can call that then 0.5 to the 6th, and our 6 factorial, we're going to put this on our calculator anyway. So we can now go to our calculator and take 0.5 to the 6th over 6 factorial. And let me grab that real quick and do that. So 0.5 raised to the 6th, and then divide that by 6. I'm going to go math over to the probability, PRB, the last one, down to option 4 is factorial. And so I'm looking at 2.701 times 10 to the negative 5. So that's going to be 4 zeros, 1, 2, 3, 4, and then we get a 217, and it's going to go on and on and on there. Now, when we round this, we have to be a little bit careful. When we round, we can never round down, because I have to think about that. We can't say, like, we can't round right here and say the error is going to be less than or equal to 0.0000217, because we don't know that it couldn't be just a tad bigger than that. So what we're going to have to do then is say that our error is going to be less than or equal to, and then wherever we want to round it, we have to make sure we round up. Okay? Okay, let's see what we can do here. Now we're going to determine how closely the 3rd degree Taylor polynomial for e to the x approximates the true value on this interval. Now you can see this interval is centered at 2, so that means that all of our derivatives have to be at 2. So we need to know what is f of 2, and of course for e to the x, all of the derivatives are going to be e to the x, which means we're going to evaluate them all at 2, which means they're all going to be e to the 2nd. So our third degree Taylor polynomial, we're going to go out to until we get an x to the third. So we're going to start with f of 2, which is e squared, and then we're going to get the first derivative, which is e squared times x minus 2 to the first, plus then we're going to get e squared times x minus 2 to the second over 2 factorial, and our third degree term is going to be e squared times x minus 2 to the third over 3 factorial. We're going to chop it off there, and that's why we're saying it's only approximately equal to e to the x on this interval. So our term, we're going to take our error term, our third degree error term, which means we're going to take everything to the next power. So we're still going to have, well, we're going to take our maximum of our, this will be the fourth derivative at some unknown number. It's going to be times x minus 2 to the fourth all over 4 factorial. Now, we know that the fourth derivative of e to the x is going to be e to the x. And we know that e to the x is an increasing function. So we know that on the interval in question, from 1.8 to 2.2, the largest that the fourth derivative could be anywhere on that interval is going to be at the right endpoint. And so that's going to be at e to the 2.2 power. Does that make sense? So when we're doing our error bound, we know that this, whatever this is, we don't know, well, we do actually in this case know the c is going to have to be e to the 2.2. So we don't know that this will get us equality, but we do know that our error is going to be less than or equal to e to the 2.2 is what we're going to replace this by. Now, we want to know what's the largest this could be on the interval. Well, again, x minus 2 to the second will be its largest at that biggest number. So we're going to get 2.2 minus 2 to the fourth power, and 4 factorial is going to be 24. So we know that our error is going to be less than or equal to e to the 2.2. 2.2 minus 2 is going to be 0.2 to the fourth over 24. So when we go to our calculator, this is going to be, it's going to be like 6.01667 blah, 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 times 10 to the negative 4. So that's going to have 3 decimal places. It's going to be 601,666 and so on. So we're going to say that that error is going to be less than or equal to, and I'm going to call that a 602. And that we can say with confidence and safety that the error will be less than or equal to that. Okay, let's scroll up and see if we can do another example. So this is actually off an earlier AP exam. Kind of a tough one, but this is probably about how hard it can get, I would say, for a Taylor polynomial question. So f of x is sine 5x plus 4. P of x is going to be the third degree Taylor polynomial about 0. So we want to use the Lagrange error bound. Now, this can be confusing, this notation, but what this is really saying is the difference between the function at 1/10 and our approximating Taylor polynomial is going to, at 1/10, is going to be less than 1/100th. So for us, that means we're trying to show the error is less than or equal to 0.01. And we're going to do our Lagrange error bound. So that's going to be that, and since we said a third degree, we're looking for R3 of x. Now, to do this, we're going to have to do a little bit of work. This is centered at 0, but we can't just take our Maclaurin series for sine x and try to translate it, because our derivatives at 0 aren't going to be those nice ones that we're used to. So we can see that f of 0 is going to be actually the sine of pi over 4. And we don't really have to do this, but it's just kind of to make the point. And f prime of x is going to be now a chain rule derivative. So that's going to be the cosine of 5x plus pi over 4. Then because of the chain rule, we're going to get an extra 5 in there. See what's happening here? Now our second derivative then is going to be, the derivative of cosine is going to be a negative. We're going to get a sine again of 5x plus pi over 4. And we had that 5 in front, but with the chain rule, we're going to get another 5. So now that's going to be up to 25. This is kind of an important thing when we're going to go in a minute towards trying to see what's the largest our derivative can be on our interval. So now the third derivative, we're going to get cosine of 5x plus pi over 4. And chain rule, we're going to get another 5. So now we're at negative 125. Now our r sub 3 of x is going to be a fourth derivative at some unknown number. This is centered at 0, so it's going to be x to the fourth. And 4 factorial is going to be 24. So we're looking for what is the largest that our fourth derivative could possibly be on at all, forever. So when we take our fourth derivative, we can see that we're going to get now another negative. Doesn't really matter, it's the sign. 625 sine of 5x plus pi over 4. This is what we're trying to find the maximum of. Well, we know that the largest the sine of anything can be is 1. So the largest that 625 times that could be is going to be 625. So that's what we're going to use as our replacement for this. Okay? So now we're going to say then that our error, so I'm going to just call this thing right here our error. So our error is going to be less than or equal to 625, and then that's going to be x to the fourth over 24. Now here, different than the problem that we did earlier, where they gave us an interval, it might be at first glance, what is our interval that we're trying to find this maximum value of, but the clue, it's actually given right here, that we're just trying to approximate the polynomial at 1/10, so at 0.1. And so since we're interested there, that's the value we're going to plug in for x to the fourth. So our error is going to be less than or equal to 625 times 0.1 to the fourth all over 24. And when you do that, you're going to get on your calculator like a 0.0026 on and on and on there, and that is clearly less than the 1/100th that we were asked to show. So we have done what it is we wanted to do. Okay? These are tough.